Okay, we're going to continue now, sort of from where Wilfrid left off in the last talk, talking about these GUE processes and their limits as semicircular laws, why it's important for us to consider the space of non-commutative laws, and then we'll get into why the theory of viscosity solutions is useful, because we don't really have smoothness in the space of non-commutative laws, and viscosity solutions gives us tools to deal with that. So Wilfrid introduced this process, which is a random variable valued in the space of d tuples of self-adjoint n by n matrices. And we want to understand its limit as n goes to infinity. And we can consider these as inside of some, larger tracial von Neumann algebra, but we actually don't have any hope for a limit within the tracial von Neumann algebra. And we have to consider this sort of topology on a quotient space, which is the non-commutative laws. So we consider the matrix algebra and the normalized trace as a von Neumann algebra. Tracial von Neumann algebra. And the way we're going to get this object to converge, I guess I'll state it as a theorem, that if we look at the law, so this is going to be an element of, call it sigma d2, which are these non-commutative laws of d variables with finite second moments. And this converges to the law of a process, semicircular process, which we'll introduce. And this convergence happens sort of weakly, almost surely, in the sense of the sort of strong law of large numbers, where this object is random. It's kind of like a random measure, except now we're in the non-commutative laws. And this one's actually deterministic, but there's sort of this free randomness that is maintained. So okay, gonna go to talk about this, what this process is, and just like a quick reminder of this space of non-commutative laws, probably in a slightly different way. We want to view this space, or one way to view this space.
You mentioned this is due to
Voiculescu? Yeah, Voiculescu and many others have worked on this and many other forms of these kind of results. So one way to define this space is as a quotient space of the tracial von Neumann algebra, so this notation we'll use to write tracial von Neumann algebra, which consists of the C-star algebra and the tracial state, modulo some relationship, where to define this relationship, we have to consider kind of the embeddings of tracial von Neumann algebra. So x in a tracial von Neumann algebra is equivalent to y. In another tracial von Neumann algebra, if there is this map, sorry, these are all d tuples of self-adjoint elements. I forgot to write this. L2 space is this GNS space, which is a Hilbert space associated to the von Neumann algebra with this tracial inner product. And these are the d tuples of self-adjoint elements. And if there is, so I'm going to do this very quickly. It's not, it is very important for the talk, but don't expect everyone to understand all the details immediately. So these are sort of inclusions, right? We want to think of A as a subalgebra of C and B as a subalgebra of C of some larger von Neumann algebra C. And that's going to define sort of an embedding in these spaces. And we want and then these extend in a natural way to the Hilbert space. And
You mean that A is generated by X?
no.
But then you
This is not.
That's fine because you can always extend the embedding to a larger algebra by amalgamating. You don't have to assume that it's generated by.
Yeah, so we could talk maybe afterwards about some of the details. Probably going to run over a lot of details here. But right, this is how we view this as a quotient space. And right, the quotient metric is the Wasserstein metric. And then right, very important to mention is that and then these lambda embeddings are just the natural inclusion into the quotient space. And an important thing to mention is that right, this space actually contains, at least in some sort of isomorphism as the commutative laws, which are really just the Wasserstein space. I mean, in fact, right, the metric is the same as the Wasserstein metric on this subset. And to go slightly into more detail about this, right, the von Neumann algebra that correspond to commutative laws are going to be can be given by these probability spaces where like right F is a sigma algebra, and right I wanted to. This is going to show up right a lot in this talk. Is we have to consider these type of inclusions and their adjoint, and it's very familiar if you're done much probability. You can consider a subalgebra, a subsigma algebra G. There's a natural inclusion from the random variables that are measurable with respect to, right, so these are, sorry, this is some probability measure, right, these are the random variables measurable with respect to this. Sigma algebra, if you consider a subsigma algebra, there's a natural inclusion of the subsigma algebra, the random variables, into the larger space of random variables. And the adjoint, so the adjoint with the L2 inner product is the conditional expectation right, of X conditioned on the sigma algebra G. So right, this is a very natural, this is right, the object we always consider in probability theory, right? It generalizes exactly to just the adjoint of these types of embeddings, and here we really see the connection between the sigma algebra and the von Neumann algebra, which is going to be really important for understanding things like this semicircular process. Now, okay, say what it is. So first off, I'm going to be a bit more technical probably than some of the other. When I gave an introductory talk at the beginning, it's going to go into a little more of the technicalities, and so in particular with the non-commutative filtration are the increasing subalgebra you can see this as directly a generalization of what a filtration is in for stochastic processes, and so we define that process ST, let's say, is a semicircular process with respect to the filtration right? In a lot of cases, we just going to take this as the algebra sort of generated by this process, but for various reasons in stochastic control, it's useful not to do that and to allow for larger algebra. So even though it slightly looks more technical, maybe. So for this to be a semicircular process, we start at 0 for each time and component. We want this to have a semicircular distribution with mean 0 and variance t minus s, and that's just this distribution that looks like that, right? We're in a single variable, so we can just think of that as like a measure, and this is the replacing now the Gaussian, as everything here would give us a Brownian motion. If we change this to Brownian to a Gaussian in the next in what will be come up in the next item. Well, not the next item, actually. This next item is that we want ST to be in the algebra of the filtration at time t. And we want something to replace independence, which is that we look at this algebra generated by these increments for, I equals 1 to d are freely independent and freely independent of the algebra at time s. I guess we're assuming t is greater than s. So the future increments, right? This is a condition, standard condition for Brownian motion, except we've changed it to freely independent, and we want to understand that for subalgebra. So okay, going to define that next. So that's right, it's a condition for subalgebra if for any elements xk in BIK such that, hopefully I get this right, so trace is 0 and the adjacent variables are in different subalgebra, then the trace of x1, x2, x m, I didn't really say how many there are, should be equal to 0. Yeah, thank you, not equal to. So okay, it's a little bit hard to tell from this definition what this exactly means. Just to give a very quick example, that is kind of reminiscent of the calculations we see a lot of, is that if S, say S is a semicircle. I mean, really the only thing I'm going to use about this is that it has mean 0 and freely independent. And so the sigma algebra, or the, sorry, von Neumann algebra generated by S is freely independent from the von Neumann algebra generated by some other elements x and y. Then, right, we can use this to compute things like S, X, S, Y. And right, what we get is that whatever relations that might be between x and y kind of disappear because it gets multiplied by this thing that's independent, and we get the variance of the semicircle multiplied by the trace of x and the trace of y, which is a pretty easy to do calculation from this definition. And we also see that there's sort of a natural way to combine von Neumann algebra related to free independence, which is the free product. So given two von Neumann algebra A and B, I'm not going to go too much into this, but this is like used a lot in our paper. There's a free product where elements of A and B, or where it's A and B, which can be viewed as subalgebra, are freely independent. So we can always kind of combine them in this way, and actually often it's necessary to do this sort of amalgamated free product where they also share a common subalgebra. We won't get into those details too much. And we can really contrast this with the other construction, which is that you can also create a tensor product algebra. And right, this is the algebra where elements of A and B commute with each other. So these are kind of very much opposite things. And in the case when A and B are themselves commutative algebras, right, this would construct an algebra where elements of A and elements of B are classically independent. So all of these things kind of get put into this algebraic context now. All right, so now we're going to go to the control problem that Wilfrid was talking about in his talk, which was the limit of these sort of random matrix control problems. We have sort of dynamics, which are given by a sort of a type of stochastic and so here we see our semicircular process showing up. And then if you remember from Wilfrid's talk, we were also keeping track of a single classical Brownian motion, which will be multiplied by the identity in our von Neumann algebra for each component. And I think Wilfrid focused on the case that, right, there's this control drift term, which kind of corresponds to, well, we'll see how it kind of corresponds to these like vector fields, but the main case is that this is just our control, so we're going to have these controlled processes, alpha, which we optimize over. And in this case, right, we can just write this, we can integrate everything, and just, so I won't define exactly what that means, but in this case, if we're starting at and we should also have here an initial condition for some d tuple x naught. And so, right, we want to consider a control problem where we're optimizing over our control processes alpha, but, right, we don't want to either fix our semicircular process or our von Neumann algebra. And so the problem that we look at is right, this cost function given an initial condition x naught and like an initial time t naught as the expectation. So this expectation is with respect to the probability space for the what we call the common Brownian motion, and remaining time of some Lagrangian function plus some terminal cost, oops. And we're going to take an infimum, and so infimum is really going to be, we want to choose these filtrations. We want to choose alpha t so that they're in the so that they're kind of adapted to these filtrations, so that they're in the algebra coming from this filtration, which gives them the correct relationship with the semicircle process. So ST is a semicircle process with respect to this filtration. And then, of course, xt solves our dynamic equation over here. And so this is actually, right, this is like kind of a really still a direct generalization of what a common approach is for stochastic control problems. Also, it's kind of called this like probabilistically weak formulation, where you allow this sort of freedom to choose the Brownian motion and the filtration. And in the classical theory of stochastic optimal control, this turns out to be really essential when you kind of consider control problems where there's dependence of the control variable on the coefficient of the Brownian motion. It's less important in this case, actually, but that's why people in stochastic control go to this kind of type of weak formulation. But for us, it's actually even more essential to use this type of formulation. in order for this kind of to make any sort of sense, there need to be more conditions on this sort of data B, L, and G that I've written. And so in particular, we want to consider terrestrial functions. So I'll just say some of it. I don't know if we're going to say all of it. So assume L, or so LA. Now, right, we're kind of thinking of this as a collection of functions for any von Neumann algebra, and this is tracial if whenever we have one of these inclusions of von Neumann algebras that preserves trace and all of that, we have the correct inclusion on our function. And actually, right, this condition is really equivalent now if we think of the space of non-commutative laws as a quotient space to thinking of this function L as a space of, as a function on the non-commutative, like 2D laws, considering the joint distribution of x and alpha. And same for, so we're going to assume the same thing for G. For B, it's slightly different. I'll just to write it for G, it looks like this. Only one argument. And then the B alphas are kind of related to what's going to be like the tangent space for the non-commutative laws. And this is a tracial vector field. And it satisfies so now you look at the inclusion of the vector field with the same sort of embedding should correspond to this vector field in the B algebra evaluated at the inclusion of the arguments. So these kind of objects are could be naturally associated with the tangent space of the non-commutative laws of two variables or 2D variables. And right, we saw the sort of geometry talked about earlier, right? The thing to take into account is that now we're on the quotient space, right? It's the quotient of like these really nice L2 spaces, but it's not smooth. It's not like a smooth Riemannian manifold due to the quotient. It's non-smooth. And that's already a big challenge, right, in the classical Wasserstein case. Okay, try to say this really quickly. Also, one other assumption is we have this assumption that alpha mapping to, so we're just going to look at the alpha part, should be E-convex, which means that it's sort of convex in the L2 space and that it satisfies that LA of the x and the expectation of alpha should be less than or equal to LB of the. So this is kind of something you would get from from Jensen's inequality when you think of this as a conditional expectation. And we want to also assume this is E linear, which is the same sort of condition where now we have this expectation also on the right-hand side. So, right, these are like important analogues when we want to do things involving convexity. Okay, so our main point of this talk is to answer sort of what equation does this V solve? So I'm skipping a lot of our paper now where we have to address like sort of a bunch of other sort of more technical assumptions about continuity and stuff on all these things and demonstrate that the dynamics are like well posed. We're going to skip over some of that. So I guess I'm going to write the equation. It's not going to be correct, but we'll try to figure it out. But yeah, before we correct it, we're going to have to figure out what all the terms are. So okay, first term, ordinary partial derivative in time. Now we have a Hamiltonian function, x minus grad v of t and x. And we have a term corresponding to this. Wait, okay, before I say that, right, given these assumptions, let me just say x maps to v alpha t naught x is a tracial function. I guess that's a theorem in our paper, right? Given essentially these assumptions, that makes this a tracial function.
Don't you want to minimize over the set of
Yeah.
algebra?
Yeah, that's the part where this is not correct.
That's the theorem, before the theorem is true.
Yeah. Okay, great. So we're minimizing over von Neumann algebra, filtrations, control policies, and semicircular processes. Yeah, we got to minimize over all of these things, with some technicalities of which von Neumann algebras we actually want to consider. We want the L2 space to be a nice separable Hilbert space. So then this, right, really makes this V a function on the space of non-commutative laws. And so that's why we're kind of trying to understand this as an equation of functions on the space of non-commutative laws. And like the most weirdest part about it is, right, what is going to be the operator, like the generator, for this semicircular process? So that's going to be this first term I'm writing here. There's some operator on these functions corresponding sort of to the generator, the Laplacian, for the semicircular process. And then there's an operator corresponding to the generator for the Brownian motion process. All right, so this is not going to be quite right, but this is like basically the equation that we want it to solve or expect it to solve. And we got to define all of these things, which I'll try to do pretty quickly. So that Hamiltonian is the supremum over over alpha in L2 of a d self-adjoint of the drift with p minus right, so this is a L2 inner product on the D tuples that we're considering, and essentially, right, the Legendre-Vinchel transform sort of generalized for a drift function B. And under these kind of assumptions we laid out, this is actually a tracial function. So this term, So under those assumptions, we get a tracial function that kind of comes from this E-linearity and E-convexity, makes this tracial. And then, all right, all the other, we make a bunch of other assumptions in the paper, making this sort of like uniformly continuous. What part of the ideas of viscosity solutions is we shouldn't need all of these assumptions. We should be able to handle very general cases, but we kind of try to handle the easy case where there's sort of uniform continuity as well and stuff like that. And it's tracial and it's E-convex with respect to this variable. You know, the difficulty thing, though, is in this equation, right? We would want all the terms in this equation to be kind of tracial as well. But this term already is not going to be tracial. The gradient of a tracial function is not a tracial vector field. It would instead be something like a co-tracial vector field. So it's already not quite making sense that this equation can hold for any von Neumann algebra. The next term. Okay, next term I'll handle is this term. So once we fixed the von Neumann algebra, can define the Hessian just with respect to the Hilbert space. And then we're going to evaluate it at elements that are just the identity, right? So this is just identity in each component. Turns out this is tracial. So actually, this term is kind of like, in some sense, the easiest to handle. It makes sense to put a one-dimensional Brownian motion inside of any von Neumann algebra, and we get like a tracial function from this Laplacian. And then the hardest term to handle probably is this free Laplacian term. Obviously, we need some smoothness to be able to define this Hessian. So we're going to define this for smooth functions. We're usually not going to expect to get smooth functions, but that's where the viscosity solution theory comes in. So maybe I should say this. For some sort of smooth functions, we can define these objects. And this one we can define similarly with the Hessian evaluated at some special elements here, but now the elements are going to be SIE, I, SIE, I. So these are just going to be, these EIs are just going to be the identity in the ith component. And we want SI should be, so what makes this definition work is that we're going to not evaluate this in the original algebra where we may or may not have, we want some sort of like independent semicircle laws, but instead we can, if V is a tracial function, work inside of some larger algebra combined by the free product of B, where S in V is a semicircle.
The S there is for t equals 1 or arbitrary S or?
What do you say?
The S there, is this for t equals 1 or?
So here in this formula, S is just some is just
an
some
arbitrary?
semicircle D tuple
Okay,
With variance 1?
with variance 1.
yeah, that's what I was
The
asking.
point is that it has to be free from everything, right? Because
Right.
it's in the future somehow, and so
Yeah, so I guess, yeah, T equals 1. And so this is a nice way to write it. Like, right, it's actually, this term, I think, makes this a tracial function. And actually, you can relatively easily evaluate it. The problem is it's not defined, or it's not defined on a single von Neumann algebra. To define it in this general way, we have to start with a tracial function. And that introduces a lot of difficulties because the regularity assumptions you would want are not always compatible with like Hilbert space regularity. So you can't really consider just like smooth functions on the Hilbert space. You don't get enough functions, but all right, we'll just finish with saying what is then our solution. So actually now we have this thing, it kind of, all right, if we consider this term, why is this difficult, right? The example which we could want to think of is like, this is just the norm of the gradient squared plus some function of x or something. So the function of x is fine, but the norm of the gradient squared, right? You can think if you have if you look in a smaller sigma algebra, you're going to lose a lot of the directions for the gradient. And so that's going to be a lot smaller than what it's supposed to be. And so, if this, yeah, so, anyways, it's basically this will be satisfied with an inequality for all von Neumann algebra, but only inequality for von Neumann algebra where you can kind of think of having a solution for the control problem. And that ends up working very nicely with this concept of viscosity solution. So what does it mean to solve it? So this is the definition of a viscosity solution. So we take this tracial function, which we can think of as being upper semi-continuous on this space of non-commutative laws. And we're going to do this, combine the subsolution and supersolution definitions by saying, respectively, its lower semi-continuous is a free, or I guess non-commutative is better. Of this equation if well, first off, we want to satisfy the right inequality with the terminal condition at the endpoint, and it's greater than or equal to for subsolutions and, sorry, subsolution, respectively, supersolution. And then for smooth tracial function, phi the equation should hold, and now I'm just going to go back over here and correct the equation.
Do you have another color?
What?
Use another color if you want to correct.
Yeah. All right, first correction is let's replace these with phi. We don't work with the actual function, sorry, we work with these test functions. And that reminds me, actually, I forgot to write something important. For smooth functions, phi tracial functions that I'm going to skip some of the definition, but touch V alpha from above at T lambda, respectively, from below. So this is the common notion in viscosity solutions applied on the space of non-commutative laws. So basically, phi should be greater than or equal to V at every point except for one at some particular law. Lambda, and then here we replace these all, the test functions with phi, where we assume all these things have been defined now. And the inequality is less than or equal to, but notice I used lambda over there. This equation has x in it. So I didn't specify a von Neumann algebra. And so here we need to take a supremum over von Neumann algebra. And lambda x equals lambda. And that's the equation, and it's less than or equal to respectively greater than or equal to, but for both the subsolution and super solution, it's a supremum of von Neumann algebra. And okay, with that definition, we proved that the value function is a viscosity solution. And in general, it's not that sensitive to which smooth functions. In general, the theory of viscosity solutions is not that sensitive to which smooth sum functions you define, although that is a challenge. And it's not clear that we made the right choice. And I'll mention why in a second. So our theorem is that our V, which is a tracial function, is a viscosity, non-commutative viscosity subsolution. And supersolution and so once we have this theory, right, we can hope that we can sort of use it to develop a framework for a lot of other problems, such as like the large deviations problems David was talking about, and other related problems. But okay, big open problem. I'll end with this sort of like open problem. In particular, for this theory to be particularly relevant, and also for the theory to go towards the direction of answering the question from Wilfrid's talk, whether this is really the correct limit of the random matrix models, it would help to have a comparison principle. So in viscosity solution theory, you usually have a comparison principle for viscosity solutions. This guarantees uniqueness amongst other things, and would basically to say that if you have a subsolution that's greater than or equal to at the endpoint and a super solution that's less than or equal to at the endpoint, you can compare those at all times. And already, like in the last couple of years, there's kind of been progress, I think, on understanding this in the Wasserstein for viscosity solutions on Wasserstein space. But I think there's still open problems on Wasserstein space, not to mention the space of non-commutative laws where things get even a bit hairier. But it would be really, really great to have that. Anyways, all right, we'll finish there. Thank you, everyone.